Major League Baseball now records information about every pitch thrown in every game of every season. Statistician Jim Albert compiled data about every pitch thrown by 20 starting pitchers during the 2009 MLB season. The data set included the type of pitch thrown, curveball, changeup, slider, etc., as well as the speed of the ball as it left the pitcher's hand. A histogram of speeds for all 30,740 four-seam fastballs thrown by these pitchers during the 2009 season is shown below, from which we can see that the speeds of these fastballs follow a normal model with a mean of 92.12 miles per hour and a standard deviation of 2.43 miles per hour. Compute the z-score of a pitch with a speed of 85.3 miles per hour. Well, a z-score is found using our z-score formula, which is x minus mu divided by sigma. So x is the data value in question, so we want a z-score of 85.3, so that's the data value. The mean of this normally distributed set of data, we had a mean of 92.12, and the standard deviation of this distribution was 2.43. So 85.3 minus 92.12 over 2.43. So that gives us if you're going to not use parentheses around the numerator, make sure to do that numerator's computation first and then divide by the denominator. Otherwise, the order of operations will give you a different answer because the division would happen first before the minus. Z-scores are typically rounded to 2 decimals, but just follow any rules given. Negative 2.81 is what I'll report here. Approximately what fraction of these four-seam fastballs would you expect to have speeds between 89 miles per hour and 90.8 miles per hour? So asking what fraction of these fastballs have certain speeds, a fraction is just another way of expressing a percentage, and a percentage can always be interpreted as a probability. So this is essentially asking for a probability. Now, we want the probability that a fastball is between 89 and 90.8 miles per hour. Both of those values are below the mean, so I'm going to try and shade them in such a way that they appear to both be below the mean, but my distribution's a little crowded here. Sorry about that. To find area under the curve, we use the normal CDF function. In the normal CDF function, it takes 4 inputs. The first two are the lower bound and upper bound of the region that is shaded, and then we provide the mean and standard deviation. So that was provided as 92.12 and 2.43. So I'll use the calculator at this point to come up with the answer. So if I hit second in vars, that takes me to the distributions menu where I find these. I've got normal CDF, 89, 90.8, 92.12, and 2.43. So that gives me a probability of 0.1939, and it's usually fine to answer normal distribution probabilities to 4 decimals, but of course follow any rules provided. And some of you may have seen a menu show up. And some of the later model calculators do that. So when you go into the distributions menu and you pick normal CDF, you may see a menu like this, and that's fine. It's just trying to help you remember what the different inputs to the function are, and also what order they go in. So if you'll notice, lower and upper, those are the lower and upper bounds of the shaded region. So of course, just put 89 and 90.8 like we did. The mean was 92.12, and the standard deviation was 2.43. When you hit paste, what it's going to do is plug those values into the normal CDF function and then give you the same answer right back out. So it's just there to help you remember the order of the inputs. Approximately what fraction of these 4-seam fastballs would you expect to have speeds below 89 miles per hour? So below 89 miles per hour, the only thing that changes here is what's being shaded. So 89 is approximately right here, and I want this area now. And that's still going to come from the normal CDF function, but the bounds on my shaded region are changing. This time I'm going from the slowest pitch possible, which don't use 0 in this case, because even though that is technically the slowest pitch possible, you're always going to start your region from -infinity up to a particular value. And that's just because statistically you need something that is statistically very small, even if it doesn't make logical sense. So it's always -infinity if we're doing area to the left. There is no -infinity key, so you need to put something just very small. And I usually use like -e to the 99, which means -1 times 10 to the 99th power. The upper bound of this region is 89, and the mean and standard deviation are still the same as they were. So we give those as our last two inputs. Second vars come down to normal CDF, and the lower bound is negative. Make sure you hit the negative key and not the minus. Second E, so second and comma gives you that E and then 99. The upper bound is 89, and the mean and standard deviation haven't changed, so I'll just leave those alone. Then press enter, and it comes up with 0.0996. And that's the probability that I'm looking for. Now, a baseball fan wishes to identify the four-seam fastballs among the slowest 10% of all such pitches. Below what speed must a four-seam fastball be in order to be included in the slowest 10%? So the only thing that changes here is we're still based off of a normal distribution with the same mean and the standard deviation, which was 92.12 and 2.43. But what we're looking for here is a little bit different. So I'm going to put the mean right here, 92.12, and these are speeds in miles per hour. So what I want is the slowest 10% of speeds. So the slowest 10% of speeds are pitches that are less than 92.12. So I'm going to put a barrier there somewhere to the left and have about 10% of the region's area to the left of it. So this value right here, X, that's what I'm looking for, which is a speed in miles per hour. It's not a probability or a percentage. So I know that I can't be using normal CDF to try and find this because that's only going to give probabilities as answers. To get something in terms of a unit that makes sense with the mean and standard deviation, I need to use inverse norm instead. An inverse norm takes three inputs. The first is an area to the left, and then the mean of the distribution and the standard deviation. So, using the calculator, second distributions come down to the inverse norm function. And if your calculator is such that you just need to put as you see it here in the function as I've written, that's fine. Just put your numbers in separated by commas. Or if you have these inputs as a menu, that's fine too. Just follow along with me. Either way, you should get, it looks like, well, pretty close to 89, so let's just round that to 89. The mean and standard deviation are to 2 decimals, so you might be requested to put, I guess, 89.01, but this is how I will report the answer. But follow any rounding rules that you're given.